So, here's something you've probably never really stopped to think about, even though it's happening to you right now, this very second. And it has been happening every single moment of your life, without a break. You are being pulled. Right now, wherever you're lying, whatever position you've settled into, there is a force acting on every single atom in your body, tugging you downward, holding you against the mattress, and it has never once let go. Not when you were born, not when you jumped as a kid, not when you flew in a plane. It was always there, quiet, invisible, and absolutely relentless. And the wild thing is, for most of human history, nobody had any real idea what it was. People could feel it, obviously. They knew things fell down. They knew rocks were heavy and feathers were light. But the question of why, what gravity actually is, how it works, what causes it, that question has turned out to be one of the deepest, strangest, most beautiful puzzles in all of science. And we're still not done solving it. So let's start at the very beginning. Not the beginning of gravity itself, because gravity has been around since the universe started, but the beginning of people trying to figure it out. And that takes us back a long, long way. The ancient Greeks thought about falling objects, and they thought about them a lot more carefully than people sometimes give them credit for. Aristotle, who lived around 350 BC in Athens, had a whole framework for understanding motion, and gravity was a big part of it. Now, Aristotle gets a bad reputation in physics sometimes because a lot of what he said turned out to be wrong. But here's the thing. His ideas weren't silly. They were actually pretty reasonable if you were just observing the world with your eyes and trying to make sense of it without any instruments. Aristotle believed that everything in the earthly realm was made of 4 elements: earth, water, air, and fire, and that each element had a natural place it wanted to be. Earth, being the heaviest element, wanted to be at the center of the universe, which he thought was the center of the earth. Water wanted to be just above earth, which is why oceans sit on top of land. Air sits above water, and fire rises above everything. So when you dropped a rock, Aristotle would say the rock was simply returning to its natural place. It was made mostly of the element earth, and earth's natural home was down at the center. That was his explanation. Things fall because they're going home. And honestly, think about that for a second. If you didn't know anything about physics and someone asked you why a rock falls, because heavy things belong on the ground, is a pretty intuitive answer. It matches what you see every day. The problem is, Aristotle took this further and made a specific claim that turned out to be really, really wrong. He said that heavier objects fall faster than lighter ones. A rock that weighs 10 times as much as another rock should fall 10 times faster. And this seems like it might be true. If you drop a hammer and a feather, the hammer definitely hits the ground first. But that's because of air resistance, not because of gravity itself. Aristotle didn't make that distinction, and for nearly 2,000 years, almost nobody challenged him on it. 2,000 years. Think about how long that is. Empires rose and fell. The Roman Republic became the Roman Empire and then collapsed. The entire medieval period came and went. And through all of that, the smartest people in Europe and the Islamic world mostly accepted Aristotle's view of falling objects. There were some dissenters, A few scholars in the Islamic Golden Age, particularly in the 11th and 12th centuries, started questioning parts of Aristotelian physics. A brilliant thinker named Ibn Sina, known in the West as Avicenna, who lived around the year 1000, developed ideas about what he called mail, a kind of acquired force that kept objects moving. And a little later, Abul Barakat al-Baghdadi, working in the 12th century, actually argued that falling objects accelerate, that they speed up as they fall, which was a direct challenge to Aristotle's framework. These were genuinely important insights, and they circulated through scholarly networks for centuries. But the full revolution in understanding gravity, the one that would eventually reshape everything, that had to wait for a very stubborn, very clever man in 16th century Italy, Galileo Galilei, born in Pisa in 1564. And you probably know the famous story. Galileo climbing to the top of the Leaning Tower of Pisa and dropping two balls of different weights to prove that they hit the ground at the same time, dramatically disproving Aristotle in front of a crowd of skeptics. It's one of the most iconic images in the history of science, and it's almost certainly a legend. His student and biographer Vincenzo Viviani told the story after Galileo's death, but there's no contemporary account of it actually happening. Galileo himself never wrote about doing it. So did he actually climb the tower? Maybe. Probably not in the dramatic way the story suggests. But here's what matters more than the tower story. What Galileo actually did in his workshop and his study was far more impressive than dropping a couple of balls off a building. Galileo's real genius was that he figured out how to slow gravity down so he could study it. See, the problem with falling objects is that they fall fast. Really fast. If you drop something from a reasonable height, it hits the ground in about a second or two. And in the 1500s, there were no stopwatches, no high-speed cameras, no way to precisely measure very short intervals of time. So Galileo came up with a beautifully simple workaround. Instead of dropping balls straight down, he rolled them down inclined planes, smooth, tilted ramps. A ball rolling down a gentle slope is being pulled by gravity, but only a component of gravity, so it accelerates much more slowly than a freely falling object. Slow enough that Galileo could actually measure what was happening, and what he found was remarkable. He discovered that the distance a ball travels down the ramp increases with the square of the time. So if after 1 second the ball has rolled, say, 1 unit of distance, after 2 seconds it's rolled 4 units. After 3 seconds it's rolled 9 units. This is the signature of constant acceleration. The ball isn't just moving, it's speeding up at a steady rate. And this was true regardless of how heavy the ball was. A heavy brass ball and a lighter wooden ball rolling down the same ramp accelerated at the same rate. Aristotle was wrong. Gravity doesn't pull harder on heavier things. Or rather, and this is a subtle but important distinction that would become hugely important later, gravity does pull harder on heavier things, but heavier things are also harder to accelerate, and those two effects cancel out perfectly. The result is that everything accelerates at the same rate. Everything. Now, Galileo didn't fully understand why this cancellation happened. He just observed that it did. But that observation, that simple fact that all objects fall at the same rate regardless of their mass, would turn out to be one of the deepest clues about the nature of gravity. It would take another 300 years and a patent clerk in Switzerland to fully unpack what it means. But we'll get there. Galileo also figured out something else that was crucial. He realized that the natural state of an object isn't rest, it's constant motion. Aristotle had said that objects naturally slow down and stop unless something keeps pushing them. Galileo argued the opposite. If you could eliminate all friction, all air resistance, all the things that slow objects down, a moving object would just keep moving forever in a straight line. This idea, which we now call inertia, was absolutely revolutionary. It completely overturned the Aristotelian worldview, and it set the stage for everything that came next, because once you understand inertia, you can start asking much sharper questions about gravity. If objects naturally move in straight lines, then gravity must be a force that's constantly deflecting them, bending their paths, pulling them into curves. Galileo published his findings on motion in 1638 in a book called Discourses and Mathematical Demonstrations Relating to Two New Sciences. He was 74 years old, under house arrest by the Inquisition for his support of the Copernican model of the solar system. The idea that the Earth orbits the sun rather than the other way around. He was nearly blind by then. The book had to be smuggled out of Italy to be published in the Netherlands. And yet it contained some of the most important physics ever written. It's one of those moments in history where you realize how much one person's stubbornness and curiosity can change the world, even when the world is actively trying to shut them up. But Galileo's work, as brilliant as it was still incomplete. He understood how things fall. He could describe the motion beautifully, but he couldn't explain why. Why do objects accelerate toward the Earth? Why does the Earth pull on things at all? What is this force, and where does it come from? For that, the world needed someone else. Someone who could take Galileo's observations about falling apples and rolling balls and connect them to the motion of the moon, the planets, the entire cosmos. Someone who could see that the force pulling you into your bed right now is the exact same force holding the moon in orbit around the Earth, and the Earth in orbit around the sun. And that someone was born on Christmas Day, 1642, in a small manor house in Woolsthorpe, Lincolnshire, England. His name was Isaac Newton, and he was, by almost any measure, one of the most extraordinary minds that has ever existed. But he was also difficult, secretive, vindictive, and deeply strange. He spent years of his life on alchemy, trying to turn base metals into gold. He wrote more about theology than he ever wrote about physics. He had bitter, decades-long feuds with other scientists, most famously with Robert Hooke and with Gottfried Wilhelm Leibniz over who invented calculus. He was not by any stretch an easy person to like, but what he did with gravity changed everything. The famous apple story, you know the one. Newton is sitting in a garden, an apple falls from a tree, and he suddenly realizes that the force pulling the apple down is the same force keeping the moon in its orbit. Like the Galileo Tower story, this one is probably embellished, but it has a stronger basis in fact. Newton himself told the story to multiple people late in his life, including his friend William Stukeley, who recorded it in 1726. Newton said, "The apple falling made him wonder. if the Earth's gravity reaches up to the top of a tree, does it reach further? Does it reach to the top of a mountain? To the moon? And if it does, is the moon essentially falling toward the Earth all the time, but moving sideways fast enough that it keeps missing? That last idea is the key, and it's worth sitting with for a moment, because it's genuinely one of the most beautiful insights in all of physics. Think about throwing a ball horizontally. It arcs downward and hits the ground, right? Now throw it harder. It goes further before hitting the ground, but it still falls. Throw it harder still. It goes even further. Now imagine you could throw it impossibly hard, so hard that as it falls toward the Earth's surface curves away beneath it at the same rate. The ball is perpetually falling, but the ground keeps curving away, so it never lands. It just goes around and around. That's an orbit. An orbit is just falling and missing the ground. The moon is falling toward the Earth right now, this very second, and it has been falling for 4.5 billion years. It just keeps missing. Newton took this insight and turned it into mathematics. And this is where things get really powerful, because Newton didn't just say gravity exists and it pulls things. He wrote down an equation, a precise quantitative law that tells you exactly how strong gravity is between any two objects anywhere in the universe. His law of universal gravitation, published in 1687 in the Principia Mathematica, says that every object with mass attracts every other object with mass, and the strength of that attraction depends on two things: how massive the objects are and how far apart they are. Double the mass of one object, and the gravitational pull doubles. Double the distance between them, and the pull drops to a quarter. It follows what's called an inverse square law. The force decreases with the square of the distance. And that word, universal, in universal gravitation, that was the truly radical part. Newton was claiming that the same law that governs a falling apple also governs the orbit of Jupiter. The same equation works for a pebble dropping into a pond and for galaxies pulling on each other across millions of light years. One law, everywhere, always. Before Newton, people thought of the heavens as fundamentally different from the earth. The celestial realm had its own rules, its own perfection. Newton demolished that distinction. The universe, he showed, runs on the same physics from top to bottom. And his equation was so accurate that scientists used it to predict the existence of the planet Neptune before anyone had ever seen it. They noticed that Uranus wasn't quite following the path Newton's law predicted, figured there must be another planet pulling on it, calculated where that planet should be, pointed a telescope at that spot, and there it was. That's the power of a good theory. It doesn't just explain what you already know. It tells you things you don't know yet. It reaches out ahead of you and says, "Look over there, you'll find something," and then you do. So by the early 1700s, Newton's framework was essentially the operating system of physics. If you wanted to calculate the trajectory of a cannonball, you used Newton. If you wanted to predict when a comet would return, you used Newton. If you wanted to figure out the tides, the shape of the Earth, the wobble of its axis, Newton, Newton, Newton. And for over 200 years, it worked beautifully. Engineers built bridges with it. Astronomers charted the heavens with it. the entire Industrial Revolution unfolded on a foundation of Newtonian mechanics. It was, by any reasonable measure, one of the most successful scientific theories ever devised. But here's the thing about gravity that Newton himself admitted he didn't understand. He could describe it perfectly. He could calculate it. He could predict it. But he couldn't explain it. He couldn't tell you how it worked. How does the sun, sitting 93 million miles away, reach across all that empty space and tug on the Earth? What's the mechanism? What's actually happening between those two objects? Newton famously wrote, in Latin, hypotheses non fingo. I frame no hypotheses. He was basically saying, look, I know this equation works. I've shown you it works. But don't ask me why it works, because I genuinely don't know. And that bothered him. It bothered him deeply. He called it an absurdity that one body could act on another through a vacuum with nothing in between. He just couldn't figure out the alternative. And for a long time, nobody else could either. So physicists did what physicists do when they have a tool that works. They used it and tried not to worry too much about the philosophical gap underneath. Gravity was an instantaneous force that acted at a distance. That was the model. You didn't need to understand the mechanism to use the equation. And the equation was spectacular. But let's sit with that discomfort for a moment, because it's actually really important. Imagine you have two magnets. You hold them near each other, and you feel that pull, that invisible tug between them. Now, you can measure that force. You can predict it. You can write down equations for it. But if someone asks you, how is one magnet reaching through empty air to pull on the other? What is physically happening in the space between them? That's a much harder question, right? Newton's gravity had exactly this problem, and it would take more than 2 centuries before someone offered a real answer. Now, in the meantime, Newtonian gravity wasn't just sitting there unchanged. Scientists were refining it, extending it, finding new ways to express it mathematically. One of the most important developments came from a French mathematician named Pierre-Simon Laplace, working in the late 1700s and early 1800s. Laplace took Newton's gravitational law and essentially turbocharged the mathematics. He developed what's called the gravitational potential, a way of thinking about gravity not just as a force between two specific objects, but as a field that fills all of space. At every point in space, you could assign a number that tells you how strong gravity is there and which direction it pulls. This was a subtle but profound shift. Instead of thinking about gravity as a conversation between two objects, the Earth talks to the moon talks back. You could think of it as a landscape. The Earth creates a gravitational field around itself, and anything that wanders into that field feels a force. The moon doesn't need to know the Earth is there. It just responds to the local conditions of the field at its location. This idea of a field might sound abstract, but it's actually more intuitive than you think. Imagine you're standing in a river. You feel the current pushing against your legs. You don't need to know where the river starts or what's causing the current upstream. You just feel the water moving past you, right here, right now. A gravitational field is similar. It's the local condition of space that tells objects how to move, And this field concept would turn out to be absolutely essential later when Einstein came along and reimagined what that field actually is. But we're not there yet. Let's stay in the 1800s a little longer, because some really interesting things were happening. One of those things was a tiny problem with Mercury. Mercury is the closest planet to the Sun, and it has a slightly elliptical orbit, not a perfect circle, but an oval. Now, the point in Mercury's orbit where it comes closest to the Sun is called its perihelion. And astronomers had noticed that this perihelion point doesn't stay in the same place. It slowly rotates around the Sun over time. The whole orbit precesses. It's like if you drew an oval on a piece of paper and then slowly rotated the paper. Each time Mercury goes around, the oval has shifted just a tiny bit. Most of this precession could be explained perfectly well by Newton's law. The gravitational pull of the other planets, especially Venus and Jupiter, tugs on Mercury and causes its orbit to shift. When you add up all those contributions, you can account for almost all of the observed precession. Almost, but not quite. There was a leftover, a tiny discrepancy of about 43 arcseconds per century. Now, 43 arcseconds per century is incredibly small. An arcsecond is 1/3600th of a degree. So we're talking about an angular shift of roughly 1/100th of a degree per century. Minuscule. But it was real, and it was consistent, and it wouldn't go away no matter how carefully astronomers recalculated. This was first identified clearly by a French astronomer named Urbain Le Verrier in 1859. And here's a nice bit of irony, because Le Verrier was the very same astronomer who had used Newtonian gravity to predict the existence of Neptune. He'd had that spectacular triumph using Newton's math to find a hidden planet. So naturally, when he found this anomaly with Mercury, he tried the same trick. He proposed that there must be another planet, even closer to the Sun than Mercury, whose gravity was causing the extra precession. He even gave it a name, Vulcan. And for decades, people searched for Vulcan. Some astronomers even claimed to have spotted it during solar eclipses, those brief moments when you might glimpse a small planet near the Sun. But none of those sightings held up. Vulcan didn't exist. And that tiny, stubborn 43 arcseconds per century just sat there, like a pebble in the shoe of Newtonian physics. Most people didn't worry about it too much. The discrepancy was so small, and Newton's law worked so well everywhere else, that it seemed like it must have some mundane explanation. Maybe the Sun was slightly more oblate than assumed. Maybe there was a ring of dust near the Sun, something like that. But it nagged at certain people. It was a crack in the foundation, even if it was a hairline crack. Now, around the same time that astronomers were puzzling over Mercury, something else was happening in physics that would eventually connect to gravity in the most unexpected way. In 1865, a Scottish physicist named James Clerk Maxwell published his theory of electromagnetism, a set of 4 elegant equations that unified electricity, magnetism, and light into a single framework. Maxwell showed that light is an electromagnetic wave, a ripple in electric and magnetic fields that propagates through space at a specific, constant speed, about 186,000 miles per second, or 300,000 kilometers per second. And here's what's crucial. Maxwell's equations said that the speed of light is the same, no matter what. It doesn't depend on how fast you're moving or how fast the source of light is moving. It's a universal constant. This created a deep problem. Think about it this way. If you're standing on a train platform and a train goes by at 60 miles per hour, and someone on the train throws a ball forward at 20 miles per hour, you see the ball moving at 80 miles per hour. The speed of the train plus the speed of the throw. Speeds add up. That's just common sense, and it's exactly what Newton's physics predicts. But Maxwell's equations were saying that light doesn't work this way. If someone on that train shines a flashlight forward, you don't see the light moving at the speed of light plus 60 miles per hour. You see it moving at exactly the speed of light. The same speed you'd measure if the train were standing still. The same speed you'd measure if you were the one moving. Always the same. This was deeply weird, and physicists spent the last decades of the 1800s trying to resolve it. Some of the greatest minds in physics, Hendrik Lorentz, Henri Poincaré, George Fitzgerald, made important progress, developing mathematical tools and partial explanations. But the full resolution came from someone who, in 1905, was not a professor, not at a prestigious university, not even really part of the academic establishment. He was a 26-year-old patent clerk in Bern, Switzerland, a guy who had struggled to find a teaching position after finishing his degree, who reviewed patent applications during the day and did physics in his spare time. His name, of course, was Albert Einstein. And what Einstein did in 1905, well, it's hard to overstate it. In a single year, he published 4 papers that each would have been a career-defining achievement for any physicist. But the one that matters most for our story is his paper on special relativity. Einstein took Maxwell's strange result, that the speed of light is constant for all observers, and instead of trying to explain it away, he embraced it as a fundamental principle of nature. He said, okay, let's just accept that the speed of light is the same for everyone, no matter how they're moving, and see what follows. And what followed was extraordinary. It meant that space and time are not the fixed, absolute stage that Newton imagined. They're flexible. They're interconnected. They stretch and compress depending on how fast you're moving. If you're moving very fast relative to me, your clocks tick slower than mine. Your rulers are shorter than mine. Not because there's something wrong with your clocks or rulers, but because time itself passes differently for you, and space itself is contracted along your direction of motion. These aren't optical illusions or measurement errors. They're real, physical effects. Time dilation and length contraction, they're called, and they've been confirmed by countless experiments since then. Every GPS satellite in orbit, right now, has to correct for relativistic time effects, or your phone's map would drift by miles within a day. And from special relativity came what is probably the most famous equation in all of science. E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy are interchangeable. They're two faces of the same coin. A tiny amount of mass contains an enormous amount of energy because the speed of light squared is such a staggeringly large number. This is why nuclear reactions release so much energy from so little fuel. This is why the sun shines. But here's what special relativity didn't do. It didn't say anything about gravity. In fact, it created a new problem with gravity. Newton's law said that gravity acts instantaneously. If the sun suddenly vanished, Earth would immediately fly off in a straight line, right that very instant. But special relativity said nothing can travel faster than light. No information, no signal, no influence of any kind can cross space faster than 300,000 kilometers per second. So which was it? Does gravity act instantaneously, or is it limited by the speed of light? They couldn't both be right. Einstein knew this. He knew that his special relativity was incomplete because it didn't include gravity. And he knew that Newton's gravity was incomplete because it didn't respect the speed limit of light. Somehow, these two frameworks had to be reconciled. And that's the problem Einstein set himself to solve next. A problem that would consume him for the next 10 years, push him to the absolute limits of his abilities, and ultimately produce what many physicists consider the most beautiful theory in all of science. But it started with something deceptively simple. It started with Einstein sitting in his chair at the patent office, daydreaming about what it would feel like to fall. He later called it the happiest thought of his life, and what he realized in that moment of imagining a person in free fall was something that connects back to that strange coincidence we noticed earlier. The fact that all objects fall at the same rate, regardless of their mass. Because if you're falling freely, if there's nothing holding you up, and gravity is the only thing acting on you, then you feel nothing. You feel absolutely nothing. No tug on your stomach, no pressure on your feet, no sense of being pulled in any direction. You are weightless. And that's not just a poetic description. It's a precise, physical statement. If you were inside a sealed box, falling freely toward the earth, with no windows, no way to peek outside, you could not perform any experiment inside that box that would tell you whether you were falling in a gravitational field or simply floating in deep space, far from any planet or star. The physics inside the box would be identical. Drop a ball in front of you, and it just floats there. Pour water from a glass, and it hangs in a shimmering blob. Your own body feels exactly as it would in zero gravity, because as far as any measurement you can make is concerned, gravity has vanished. That's the equivalence principle. And it sounds almost too simple to be important, but let it sit with you for a moment, because Einstein saw something profound hiding inside it. He realized that gravity and acceleration are, in a very deep sense, the same thing. Not just similar, not just analogous, physically indistinguishable. Here's the flip side of that thought experiment. Imagine you're in the same sealed box, but now, instead of falling, the box is sitting on the surface of the earth. You feel your weight pressing you into the floor. You feel that familiar downward pull. Now imagine a different scenario. The box is out in deep space. No planet anywhere nearby, but a rocket engine on the bottom is firing, accelerating the box upward at exactly 9.8 meters per second squared. You'd feel exactly the same thing. Your feet would press into the floor with the same force. A dropped ball would hit the ground in the same time. You could not tell the difference. No experiment you could ever perform, no matter how clever, would reveal whether you were standing on Earth or being accelerated by a rocket. Gravity and acceleration produce identical effects. Now, you might be thinking, okay, that's a neat observation, but so what? And this is where Einstein's genius really shows, because he didn't treat this as a curiosity. He treated it as a fundamental law of nature. He said, if you can never distinguish between gravity and acceleration, then they must be the same phenomenon. They're not just mimicking each other. They are, at the deepest level, the same thing. And if that's true, then anything you learn about acceleration must also apply to gravity. That's a remarkably powerful move, because we understand acceleration pretty well. It's just geometry and motion. And if gravity is equivalent to acceleration, then maybe gravity isn't a force at all. Maybe it's something geometric. But let's not get ahead of ourselves. Einstein had this happiest thought in 1907. He wouldn't publish his complete theory of general relativity until November 1915. That's 8 years of struggle, wrong turns, moments of despair, and some of the most difficult mathematics any physicist had ever attempted. The path from the equivalence principle to the finished theory was anything but straight. Let me walk you through what made it so hard, because I think the difficulty itself tells you something important about the nature of gravity. So Einstein had this beautiful insight. Gravity is equivalent to acceleration, and almost immediately he started seeing consequences. One of the first things he worked out, still in 1907, was that gravity must affect light. Think about it this way. If you're in an accelerating rocket ship and you shine a flashlight from one wall to the other, the beam travels in a straight line from the flashlight's perspective. But because the ship is accelerating upward while the light crosses the cabin, the beam hits the opposite wall slightly lower than where you aimed it. From inside the ship, the light appears to curve downward. And if acceleration and gravity are equivalent, then gravity must also bend light. A beam of light passing near a massive object should curve toward it. That was a testable prediction. And it was radical, because in Newtonian physics, light has no mass. Or at least, the question of whether gravity affects light was deeply ambiguous. Einstein was saying something definitive. Gravity bends light. And here's exactly how to check it. You wait for a solar eclipse. You photograph the stars near the edge of the sun, and you compare their apparent positions to where they normally are. If gravity bends their light as it passes near the sun, the stars should appear slightly shifted outward, as if the sun's gravity is acting like a lens. We'll come back to that eclipse, because it's one of the great stories in the history of science. But in 1907, Einstein wasn't ready to make that prediction precisely because he didn't yet have the full mathematical machinery. He knew the direction, but not the exact amount. Here's the other thing he figured out early on, and this one is maybe even more mind-bending. Gravity must affect time, not just motion through space, actual time. Clocks in a gravitational field run slower than clocks far from any mass. And again, you can see this from the equivalence principle. In an accelerating rocket, a clock at the bottom, closer to the engine, deeper in the acceleration, ticks slightly slower than a clock at the top. This is a real, measurable effect, not an illusion. And if acceleration and gravity are equivalent, then a clock on the ground floor of a building ticks slightly slower than a clock on the top floor, because the ground floor is deeper in Earth's gravitational field. Time itself runs at different rates depending on where you are in a gravitational field. This is called gravitational time dilation. And I want you to know, This isn't theoretical speculation anymore. We've measured it. In 1959, Robert Pound and Glenn Rebka, working at Harvard, measured the difference in the rate of time between the top and bottom of a 22-meter tower. 22 meters. That's about the height of a 7-story building. And they found exactly the shift Einstein predicted. Today, the GPS satellites orbiting Earth have to correct for gravitational time dilation constantly. Their atomic clocks tick faster than identical clocks on the ground by about 45 microseconds per day, because they're higher up in Earth's gravitational field, where gravity is weaker and time runs faster. If GPS didn't account for this, your position readings would drift by roughly 10 kilometers per day. So every time you use your phone to navigate to a restaurant, you're relying on Einstein's insight from 1907 about gravity and time. But knowing these consequences and having a complete theory are very different things. Einstein had the equivalence principle. He had these early predictions. What he didn't have was the mathematical framework to describe how mass and energy actually shape the behavior of space and time. And this is where the story gets really human, because Einstein was not primarily a mathematician. He was a physicist with extraordinary physical intuition. He could see the right answer, feel it almost, but translating that vision into rigorous mathematics nearly broke him. The key insight he needed, the really big conceptual leap, was that gravity is not a force pulling objects through space. Gravity is the curvature of space-time itself. Mass and energy warp the fabric of space and time, and objects move along the straightest possible paths through that warped geometry. What we perceive as the force of gravity, the apple falling, the moon orbiting, your feet pressing against the floor, is actually the natural motion of objects through curved space-time. Let me try to make that more intuitive. Imagine a stretched rubber sheet. People use this analogy a lot, and it's not perfect, but it captures something real. If you place a heavy bowling ball in the center of the sheet, it creates a dip, a curved depression. Now, roll a marble across the sheet. The marble doesn't travel in a straight line anymore. It curves toward the bowling ball, spirals around it, maybe falls in. It looks like the bowling ball is attracting the marble, pulling it with some invisible force. But there's no force. The marble is just following the curved surface of the sheet. It's taking the straightest path available to it through a geometry that's been warped by the bowling ball's weight. That's roughly what Einstein proposed. The Earth doesn't reach out and grab the moon with some mysterious force. The Earth's mass curves the space-time around it, and the moon travels along the straightest possible path through that curved space-time, which happens to be an orbit. You're not being pulled down toward the floor right now. The mass of the Earth has curved the space-time you're sitting in, and the floor is pushing up against you, preventing you from following your natural path through that curved geometry. If the floor vanished, you'd fall, not because a force grabbed you, but because you'd finally be free to follow the natural curve of space-time. You'd be in free fall. And as we said, in free fall, you feel nothing. No force. Because there is no force. There's only geometry. This is the deep reason why all objects fall at the same rate. Remember, that was the puzzle going all the way back to Galileo. Heavy things and light things fall together. Newton could describe it, but not explain it. It required the strange coincidence that gravitational mass and inertial mass are exactly equal. Einstein dissolved the puzzle entirely. Objects fall at the same rate because falling isn't about force at all. It's about following the shape of spacetime. And spacetime doesn't care what you're made of or how much you weigh. Every object follows the same geometry. Now, actually writing this down as mathematics, that was the nightmare. Einstein needed a way to describe curved four-dimensional spacetime, and the math for that is called differential geometry, specifically Riemannian geometry, developed decades earlier by the German mathematician Bernhard Riemann. Einstein was not fluent in this mathematics. He had to learn it, essentially in real time, while trying to build his theory. And he had help. His old college friend Marcel Grossmann, a mathematician at the ETH in Zurich, guided him through the thicket of tensors and curved manifolds and Christoffel symbols, all this dense, abstract machinery that Einstein needed but hadn't mastered. Between 1912 and 1915, Einstein and Grossmann worked together, published preliminary versions of the theory, hit dead ends, backed up, tried again. There were periods where Einstein thought he had it, only to discover errors. There was a particularly painful stretch in 1913 and 1914 where he convinced himself, incorrectly, that the equations couldn't be fully covariant, meaning they couldn't take the same form in every coordinate system. He actually published a version of the theory with this limitation built in, and it nagged at him, because the whole philosophical motivation of general relativity demanded that the laws of physics look the same, regardless of how you describe your coordinates. He knew it should be fully covariant. But the math kept leading him astray. And then there was the rivalry. By the fall of 1915, the great German mathematician David Hilbert had become interested in the problem. Hilbert was one of the most brilliant mathematicians alive, and he had the mathematical tools that Einstein lacked. Einstein gave a series of lectures in Göttingen in the summer of 1915, and Hilbert was in the audience, absorbing everything. By November, both men were racing toward the final equations. Einstein, working feverishly in Berlin, submitted a series of 4 papers to the Prussian Academy on successive Thursdays in November 1915. Each one refined the equations further. Hilbert, independently, was converging on the same result from a more purely mathematical direction. The question of who got there first has been debated by historians for decades. The priority dispute is genuinely complicated, and the surviving documents suggest both men arrived at essentially the same equations within days of each other. But the physical interpretation, the vision, the equivalence principle, the understanding of what the equations meant, that was unambiguously Einstein's. On November 25, 1915, Einstein presented the final form of his field equations to the Prussian Academy, and the first thing he did with them was calculate Mercury's orbit. Remember Mercury, that stubborn 43 arc-seconds per century that had tormented astronomers for over 50 years, that had sent Leverrier chasing a phantom planet? Einstein's equations, with no fudge factors, no adjustable parameters, no hypothetical hidden masses, produced exactly 43 arc-seconds per century of extra precession. Exactly. When he saw the result, he later told a friend that he had heart palpitations. He said the equations gave him the feeling that something had actually shifted in nature, that he was seeing the real machinery behind the universe. That something fundamental had clicked into place, like a key turning in a lock that no one had even been sure existed. And honestly, can you blame him? Imagine spending 8 years. 8 years of wrong turns, sleepless nights, tensor calculus that made your head swim, a priority race with one of the greatest mathematicians on the planet. And then your equations hand you back a number that matches observation to the arc-second. No wiggle room, no tweaking, just nature saying yes. But Mercury was a retrodiction. Einstein's equations explained something people already knew was a problem. To really prove general relativity, you needed a prediction, something the theory said should happen that nobody had observed yet, something you could go out and check. And Einstein had one ready. He'd actually been thinking about it since 1911, years before the field equations were finished. Light, he said, should bend when it passes near a massive object. Not because light has mass in the ordinary sense, but because mass curves the geometry of spacetime, and light follows that curved geometry. A beam of starlight grazing the edge of the sun should be deflected, nudged inward, so that the star appears to be in a slightly different position than it actually is. Now, here's where the story gets really good and a little bit dramatic, because the prediction changed. Einstein's first calculation, back in 1911, was based on the equivalence principle alone, before he had the full machinery of curved space-time. That early estimate gave a deflection of about 0.87 arc-seconds for light just skimming the sun's edge. And that number, this is important, is actually the same value you'd get from a naive Newtonian calculation if you just treated a photon as a little particle with some effective mass falling in the sun's gravitational field. So the 1911 prediction wasn't uniquely relativistic. It didn't distinguish Einstein's theory from a clever Newtonian guess. But when Einstein completed the full general relativistic calculation in 1915, the answer doubled. The full theory predicted 1.75 arc-seconds of deflection, twice the Newtonian value. And the reason it doubled is beautiful. Half the bending comes from what you might call the equivalence principle effect, the part that's analogous to Newtonian gravity pulling on the light. But the other half comes from the curvature of space itself. In general relativity, it's not just time that gets warped near a massive object. Space does too. The spatial geometry near the sun is slightly curved, slightly stretched, and that extra curvature adds an additional deflection that has no Newtonian analog whatsoever. So the full prediction, 1.75 arc-seconds, was a clean, testable, unambiguous signature of Einstein's theory. If you measured the deflection and got 0.87, Newton wins. If you got 1.75, Einstein wins. Nature had set up a beautiful experiment. The problem, of course, is that you can't normally see stars near the sun because the sun is, well, blindingly bright. You need a total solar eclipse, those rare minutes when the moon slides in front of the solar disk and the sky goes dark enough to photograph stars in the sun's immediate vicinity. Then, you compare the apparent positions of those stars during the eclipse with their normal positions when the sun is nowhere nearby, and you measure the shift. There was actually an attempt to test the 1911 prediction, the smaller one, during a total eclipse in 1914. A German astronomer named Erwin Finlay Freundlich traveled to Crimea to observe it. But here's one of those strange twists of history. World War I broke out in August 1914, just as Freundlich was setting up. He was on Russian soil as a German national, and he was briefly detained. His equipment was confiscated. The expedition was a total bust. And in hindsight, that was actually lucky for Einstein, because if Freundlich had measured the deflection and gotten the correct value of 1.75 arcseconds, it would have disagreed with Einstein's 1911 prediction of 0.87. Einstein would have looked wrong, even though his theory was actually right. He just hadn't finished the math yet. The war, in a weird way, saved Einstein from being prematurely discredited by his own incomplete theory. The test that actually happened, the one that made Einstein a global celebrity overnight, came in 1919. The British astronomer Arthur Stanley Eddington organized 2 expeditions to observe the total solar eclipse of May 29th. One team went to Sobral in northern Brazil. The other, led by Eddington himself, went to the island of Principe, off the west coast of Africa. And there's a human story here that's worth lingering on. Eddington was a Quaker and a conscientious objector during the war. Britain and Germany had just spent 4 years trying to destroy each other. The idea that a British scientist would risk his career and reputation to test and potentially validate the theory of a German physicist. That was a political statement as much as a scientific one. Eddington believed that science transcended national borders, and he put himself on the line for that belief. The conditions on Principe were terrible. It rained most of the day. Clouds rolled in just before totality. Eddington managed to get a handful of usable photographic plates through brief gaps in the cloud cover. The Sobral team had better weather, but had their own technical problems. One of their telescopes produced blurred images because the mirror had been distorted by the heat. So the data was messy. It was not the clean, decisive measurement you dream of, but when the plates were analyzed, the results pointed to a deflection consistent with Einstein's full prediction of 1.75 arcseconds, not the half-value Newtonian prediction. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. The Astronomer Royal, Frank Dyson, presented the findings. The philosopher Alfred North Whitehead was in the audience and later wrote about the atmosphere. He described it as almost ceremonial, with a portrait of Newton looking down from the wall as the assembled scientists absorbed the news that Newton's theory of gravity had been superseded. The next morning, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein went from being a respected but relatively obscure physicist to the most famous scientist in the world, practically overnight. Now, it's worth being honest about this. Later reanalyses of Eddington's data have suggested that the measurement uncertainties were large enough that the results weren't quite as definitive as they were presented at the time. Some historians have argued that Eddington, who was already a strong proponent of general relativity, may have been somewhat selective in which data he emphasized. The Sobral data from the better telescope actually gave a value closer to the full Einstein prediction, while some of the other plates were ambiguous. so was the 1919 eclipse. A clean confirmation? It was good enough to be convincing to most physicists, and subsequent eclipse measurements over the following decades tightened the result considerably. By the 1960s and 70s, radio astronomy techniques, measuring the deflection of radio waves from distant quasars as they passed near the sun, confirmed Einstein's prediction to extraordinary precision, better than 1% accuracy. So Einstein was right. But the 1919 result was more of a strong hint than a definitive proof, and the legend grew faster than the error bars shrank. And that's kind of the pattern with general relativity for the first few decades. The theory was mathematically gorgeous and conceptually revolutionary, but the effects it predicted were tiny. Tiny deflections, tiny precessions, tiny time differences. For most practical purposes, Newtonian gravity was perfectly adequate. Engineers building bridges, designing aircraft, calculating artillery trajectories, they didn't need Einstein. General relativity lived in a strange limbo, universally admired, rarely tested, and almost never practically relevant. But the theory had implications that went far beyond small corrections to orbits and light paths, and some of those implications were so strange, so unsettling, that even Einstein himself couldn't quite accept them. One of the first people to explore the wilder consequences of the field equations was a German astronomer named Karl Schwarzschild, and his story is one of the most remarkable in all of physics. In December 1915, just weeks after Einstein published the field equations, Schwarzschild found the first exact solution. Not an approximation, not a perturbation series, but an exact closed-form solution describing the spacetime geometry around a perfectly spherical, non-rotating mass. And he did this while serving on the Eastern Front in World War I, calculating between artillery barrages. He sent the solution to Einstein in a letter from the trenches. Einstein was stunned. He hadn't expected anyone to find an exact solution so quickly, and he presented Schwarzschild's result to the Prussian Academy in January 1916. Schwarzschild's solution was elegant, but it had a peculiar feature. At a specific radius from the center of the mass, a radius that depends on how much mass you're dealing with, the mathematics did something alarming. The equations developed what looked like a singularity, a point where certain quantities blew up to infinity. For an object with the mass of the sun, this critical radius was about 3 kilometers. For the Earth, it would be about 9 millimeters. As long as the actual physical object was bigger than its critical radius. And the sun is obviously vastly bigger than 3 kilometers. The singularity was safely hidden inside the object, in a region where the vacuum solution didn't apply anyway. So it seemed like a mathematical curiosity, nothing physical. But here's the question that would haunt physicists for decades. What if a mass were somehow compressed to be smaller than its critical radius? What would happen then? What would that singularity actually mean? Schwarzschild himself didn't live to explore the question. He developed a rare autoimmune skin disease on the front and died in May 1916, just months after his breakthrough. He was only 42. And the question he'd inadvertently raised, what happens when gravity becomes so strong that even light can't escape, would simmer in the background of physics for nearly half a century before anyone took it truly seriously. The answer, when it finally came, would be one of the strangest objects ever imagined by the human mind. a black hole. Now that name, black hole, it sounds so natural today, so obvious, that you'd think someone coined it the moment Schwarzschild's equations hinted at the possibility. But actually, the term didn't appear until 1967, when the physicist John Archibald Wheeler used it at a conference. Before that, people called them frozen stars, or collapsed stars, or more awkwardly, Schwarzschild singularities. And for a very long time, most physicists didn't call them anything at all, because most physicists didn't believe they were real. They thought nature would find some way to prevent a star from collapsing that completely. There had to be a safety valve, some force or process that would step in and stop the collapse before things got truly extreme. And the story of how that skepticism slowly, grudgingly, gave way to acceptance, that's one of the great dramas in 20th century physics. Let's set the stage. Through the 1920s and into the 1930s, astrophysicists were starting to understand what makes stars shine. Stars are basically enormous fusion reactors, hydrogen atoms smashing together under tremendous pressure and temperature to form helium, releasing energy in the process. That outward energy, that radiation pressure, is what holds the star up against its own gravity. It's a balancing act. Gravity pulls inward, radiation pushes outward, and as long as the fuel lasts, the star holds steady. But what happens when the fuel runs out? What happens when a star has burned through its hydrogen, fused its way through heavier and heavier elements, and finally has nothing left to burn? Gravity doesn't stop pulling, so the star has to collapse. The question is, how far? In 1930, a young Indian physicist named Subramanian Chandrasekhar was on a steamship from Bombay to England, heading to Cambridge to begin his graduate studies. He was 19 years old, and during that voyage, he did a calculation that would eventually win him a Nobel Prize, though it would take more than 50 years and cause him enormous personal grief along the way. What Chandrasekhar figured out, working through the mathematics of stellar structure using the new tools of quantum mechanics, was that there's a mass limit for a certain type of dead star called a white dwarf. A white dwarf is what you get when a star like our sun exhausts its fuel. It collapses down to roughly the size of the Earth, incredibly dense, but held up against further collapse by something called electron degeneracy pressure. This is a quantum mechanical effect. Basically, electrons resist being squeezed too close together. It's not a thermal pressure, not heat pushing outward. It's a fundamental quantum property, and it works beautifully for stars up to a certain mass. But Chandrasekhar showed that if the remnant core is heavier than about 1.4 times the mass of our sun, electron degeneracy pressure isn't strong enough. The electrons can't hold the star up. The collapse continues. That number, 1.4 solar masses, is now called the Chandrasekhar limit, and it's one of those beautiful, clean results in astrophysics. Below the limit, you get a white dwarf. Above it, something else has to happen. Now here's where the human drama comes in, and it's a painful story. When Chandrasekhar presented his findings at a meeting of the Royal Astronomical Society in January 1935, the most famous astrophysicist in the world, Sir Arthur Eddington, the same Eddington who had confirmed Einstein's light-bending prediction in 1919, stood up and publicly ridiculed him. Eddington essentially said the result was absurd, that there must be a law of nature preventing stars from collapsing beyond the white dwarf stage. He didn't have a specific physical mechanism to point to. He just felt, on almost aesthetic grounds, that the universe couldn't be that strange. And because Eddington was Eddington, a towering figure, enormously respected, his dismissal carried enormous weight. Chandrasekhar was devastated. He was a young man from a colonial country, facing down the most powerful voice in British astrophysics, and the community largely sided with Eddington. Not because Eddington's physics was right, it wasn't, but because his authority was overwhelming. Chandrasekhar eventually moved to the University of Chicago, continued his brilliant career, and was vindicated decades later. But the episode delayed serious investigation of stellar collapse by years, maybe a decade or more. Think about that. One man's prestige, one moment of intellectual arrogance, slowed down our understanding of some of the most extreme objects in the universe. Science is a human enterprise, and sometimes the humans get in the way. So what does happen above the Chandrasekhar limit? Through the 1930s, a few physicists pushed forward despite the skepticism. In 1934, Walter Baade and Fritz Zwicky, Zwicky being one of the most colorful and combative characters in the history of astronomy, proposed that when massive stars die, they could collapse into what Baade and Zwicky called neutron stars. The idea was that if you squeeze matter hard enough, the electrons get forced into the protons, turning everything into neutrons. And now you have a star held up by neutron degeneracy pressure instead of electron degeneracy pressure. A neutron star would be astonishingly dense. A teaspoon of neutron star material would weigh something like 1 billion tons. The whole thing would be maybe 10 or 15 kilometers across, roughly the size of a city, but containing more mass than the sun. It's almost impossible to picture, but that's what the physics predicted. And then, in 1939, Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, along with his student George Volkoff, and, in a separate paper, with Hartland Snyder, took the next step. Oppenheimer and Volkoff showed that neutron stars, like white dwarfs, have their own mass limit, above roughly 2 to 3 solar masses. The exact number is still debated today, but it's in that range. Even neutron degeneracy pressure fails. And Oppenheimer and Snyder's paper, published in September 1939, the very same month that Germany invaded Poland and World War II began, showed what happens next. They demonstrated, using general relativity, that a sufficiently massive star would collapse without limit. Nothing stops it. It just keeps falling inward, past the Schwarzschild radius, and from the perspective of an outside observer, the surface of the collapsing star appears to slow down and freeze at that critical radius, its light redshifting into invisibility. From the perspective of someone falling with the surface, well, they'd pass right through the Schwarzschild radius and continue falling inward toward the center, where the mathematics predicts infinite density, a singularity, a point of genuinely infinite curvature. Here's the thing. This paper by Oppenheimer and Snyder is, in hindsight, the birth of black hole physics. It's the first rigorous demonstration that general relativity predicts these objects must exist, given sufficient mass. But almost nobody paid attention. The world was going to war. Oppenheimer himself was about to be consumed by the atomic bomb project, and even among the physicists who did read the paper, there was a widespread feeling that this was a mathematical artifact, not a physical reality. Surely something would intervene. Surely nature wouldn't allow such an absurdity. And so, black holes went back into hibernation. For nearly 20 years, from the early 1940s through the late 1950s, almost no one worked on gravitational collapse or the extreme predictions of general relativity. The field was, as some historians have put it, a backwater. The brightest minds were working on nuclear physics, quantum electrodynamics, particle physics, fields where you could do experiments, get results, build things. General relativity was seen as beautiful but impractical, a monument to Einstein's genius that had very little to do with the real world. The revival began in the late 1950s and accelerated through the 1960s, and it happened for a mix of reasons: new mathematical techniques, new observational discoveries, and a new generation of physicists who weren't intimidated by the old guard skepticism. One of the key figures was John Wheeler at Princeton, who did more than anyone to make general relativity respectable again as a field of active research. Wheeler trained a generation of students, organized conferences, asked provocative questions, and, as I mentioned, gave black holes their name. He had this gift for vivid language that made exotic physics feel urgent and real. But the real breakthrough in understanding came from a quieter figure. In 1963, a New Zealand mathematician named Roy Kerr found something extraordinary: an exact solution to Einstein's field equations describing a rotating black hole. Now, Schwarzschild's solution from 1916 described a non-rotating, perfectly spherical black hole, which is a useful idealization, but not very realistic. Real stars rotate. When they collapse, they should form rotating black holes. And for nearly 50 years, nobody could solve the equations for that case. Kerr did it, and his solution revealed a structure far richer and stranger than Schwarzschild's. A rotating black hole doesn't just have a point singularity at the center. It has a ring singularity. It doesn't have one event horizon. It has two, an outer and an inner one, and it drags space-time around with it as it spins, in an effect called frame dragging, creating a region outside the event horizon called the ergosphere, where space-time itself is pulled along so forcefully that nothing can remain stationary. You'd be carried along like a leaf in a whirlpool, even if you fired your rockets at full thrust against the rotation. The Kerr solution was a masterpiece, and it came at exactly the right time, because astronomers were starting to find things in the sky that demanded extreme explanations. In 1963, the same year Kerr published his solution, Martin Schmidt at Caltech identified the first quasar, an object called 3C273 that looked like a faint star but turned out to be billions of light years away, shining with the luminosity of an entire galaxy from a region no bigger than our solar system. The only mechanism anyone could think of that could produce that much energy from that small A space was matter falling into an enormous black hole. Not a stellar mass black hole formed from a single collapsed star, but a supermassive black hole, millions or billions of times the mass of the sun, sitting at the center of a distant galaxy. And suddenly, black holes weren't just mathematical curiosities anymore. They were the only explanation that fit the data. Then, in 1967, Jocelyn Bell Burnell, a graduate student at Cambridge, discovered pulsars, rapidly pulsing radio sources that turned out to be rotating neutron stars, sweeping beams of radiation across the sky like cosmic lighthouses. This confirmed that neutron stars were real, not just theoretical constructs. And if neutron stars were real, then the mass limit above which they must collapse further was real too, which meant that black holes, or something very much like them, had to exist for sufficiently massive stellar remnants. Through the late 1960s and 1970s, the theoretical picture filled in rapidly. Roger Penrose proved in 1965 that singularities aren't just artifacts of perfect symmetry. They're inevitable consequences of gravitational collapse under very general conditions. This was a profound result. You couldn't escape singularities by arguing that real stars aren't perfectly spherical or perfectly uniform. Once enough mass collapses past a certain point, a singularity must form. Period. Penrose would eventually share the 2020 Nobel Prize in Physics for this work, more than half a century after he did it. Stephen Hawking, working closely with Penrose, extended these singularity theorems in the other direction, backward in time, showing that the universe itself must have begun in a singularity, what we call the Big Bang. And then, in 1974, Hawking made perhaps his most famous discovery, that black holes aren't perfectly black. Through a subtle quantum mechanical process involving the creation of particle-antiparticle pairs near the event horizon, black holes slowly radiate energy. They have a temperature. They glow incredibly faintly. And over unimaginably long timescales, far longer than the current age of the universe for any black hole we know of, they evaporate completely. This is Hawking radiation, and it created a puzzle that physicists are still arguing about today, because it raises a deep question about whether information that falls into a black hole is truly lost forever, which would violate a fundamental principle of quantum mechanics. That tension between general relativity and quantum mechanics, playing out most dramatically at the event horizon of a black hole, is one of the biggest unsolved problems in all of physics. But let's come back to something more tangible for a moment, because all of this theory would mean very little if we couldn't actually observe these objects. And the story of how we went from theoretical prediction to direct observation is one of the most patient, painstaking detective stories in all of science. Because here's the thing, you can't just point a telescope at the sky and see a black hole. By definition, the thing doesn't emit light. It's a region of space where gravity is so intense that nothing escapes. So how do you find something that's invisible? You look for the effects it has on everything around it. Think of it like this. Imagine you're in a dark room, and somewhere in that room, there's a drain in the floor, and water is flowing across the tiles. You can't see the drain, but you can see the water swirling, accelerating, disappearing. You can hear it. You can feel the pull if you step close enough. The drain reveals itself through what it does to everything nearby. That's essentially how astronomers found black holes, not by seeing them directly, but by watching what happens to matter, light, and other stars in their vicinity. The first really compelling candidate came in the early 1970s, and it involved a source of X-rays in the constellation Cygnus. This object, called Cygnus X1, had been detected by X-ray instruments carried on sounding rockets back in 1964. Now, X-rays from space are interesting because they tell you something is extremely hot. We're talking millions of degrees. And the question was, what could possibly be generating that kind of energy? By the early 70s, better observations showed that the X-rays were coming from a region very close to a visible star, a blue supergiant called HDE 226868. And this star was wobbling. It was being tugged back and forth by something massive that you couldn't see. By measuring the wobble, the Doppler shift in the star's spectral lines as it moved toward and away from us, astronomers could estimate the mass of the invisible companion. And the number they got was somewhere around 8 to 10 solar masses. Way too heavy to be a white dwarf, which tops out around Chandrasekhar's limit of 1.4 solar masses. Way too heavy to be a neutron star, which can't be much more than about 2 or 3 solar masses. The only thing it could be, given that mass and the fact that it was invisible, was a black hole. Now, the X-rays made sense too. If a black hole is orbiting close to a massive star, it can strip gas off the outer layers of that star. The gas doesn't fall straight in. It spirals, forming what's called an accretion disk, a swirling disk of material orbiting the black hole faster and faster as it gets closer. And as the gas spirals inward, friction heats it up enormously to millions of degrees, hot enough to radiate X-rays. So the black hole itself is dark, but the material screaming around it just before it crosses the event horizon is one of the brightest things in the universe. It's like the drain analogy. The drain is dark, but the water swirling into it is moving fast enough to glow. Cygnus X1 became the subject of a famous bet between Stephen Hawking and Kip Thorne. Hawking bet that it wasn't actually a black hole. Which seems counterintuitive, right? Hawking had spent years studying black holes theoretically. But he said the bet was an insurance policy. If black holes turned out not to exist, at least he'd win the bet and get some consolation. Thorne bet that it was a black hole. By 1990, the evidence had become overwhelming, and Hawking conceded. The story goes that he broke into Thorne's office while Thorne was away and signed the bet, conceding defeat. It's a charming little moment in physics history. Two friends, one of the deepest questions in science, and a wager settled with a grin. But Cygnus X1 was just the beginning. Over the following decades, astronomers found more and more of these X-ray binary systems, pairs where a visible star was being slowly devoured by an invisible, massive companion. Each one added to the case. And then the evidence started coming from a completely different direction: the centers of galaxies. Remember those quasars that Martin Schmidt identified in 1963? Those impossibly bright objects at cosmological distances? By the 1980s and 1990s, the consensus had solidified that quasars were powered by supermassive black holes at the centers of distant galaxies. Black holes, not of 10 solar masses, but of millions or even billions of solar masses. And the natural question became, is there one at the center of our own galaxy? The answer came through decades of meticulous observation, and the key figures here are Andrea Ghez and Reinhard Genzel, who independently led teams tracking individual stars at the very center of the Milky Way. The center of our galaxy, in the direction of the constellation Sagittarius, is shrouded in dust. You can't see it in visible light, but you can observe it in infrared, which passes through dust more easily. Starting in the early 1990s, both teams used increasingly powerful infrared telescopes, equipped with adaptive optics that corrected for the blurring of Earth's atmosphere, to track the motions of stars orbiting very close to a compact radio source called Sagittarius A star. And what they found was remarkable. These stars were moving fast, really fast. One star, designated S2, completes a full orbit in just about 16 years, and at its closest approach, it's screaming along at nearly 3% the speed of light, passing within about 17 light hours of whatever is sitting at the center. By tracking these orbits year after year, plotting them out with extraordinary precision, Gez and Genzel's teams could calculate the mass of the central object. The answer? About 4 million solar masses crammed into a region smaller than our solar system. There is simply nothing in known physics, other than a black hole, that can pack that much mass into that small A space. Gez and Genzel shared the 2020 Nobel Prize with Roger Penrose. Penrose for the theoretical proof that singularities must form, and Gez and Genzel for the observational proof that a supermassive one actually exists at the heart of our galaxy. And then came the image. On April 10th, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Not a simulation, not an artist's impression, an actual image, reconstructed from radio wave data collected by a network of telescopes spanning the entire globe, effectively creating an Earth-sized virtual telescope. The target was the supermassive black hole at the center of the galaxy, M87, a monster of about 6.5 billion solar masses, sitting 55 million light-years away. The image showed a bright ring of hot, glowing gas surrounding a dark central shadow. The silhouette of the event horizon against the luminous accretion flow behind it. The size and shape of that shadow matched the predictions of general relativity with stunning precision. Einstein's equations, written down in 1915 in a Berlin apartment, predicted what a black hole shadow should look like. And in 2019, we saw exactly that. 3 years later, in May 2022, the same collaboration released an image of Sagittarius A star, our own supermassive black hole, the one Gez and Genzel had been orbiting stars around. This one was actually harder to image, even though it's much closer, because it's 1,000 times less massive than M87's black hole, which means the gas swirling around it changes on timescales of minutes rather than days. It's like trying to photograph a puppy versus a sleeping cat. The smaller one won't hold still. But they did it. And again, the ring of light, the dark shadow, the confirmation of general relativity. So think about the arc of this story for a moment. From Schwarzschild's mathematical curiosity in 1916, dismissed by most physicists as a quirk of the equations, to Oppenheimer's proof that collapse was inevitable, ignored because the world was going to war, to decades of skepticism and debate, to Wheeler finally giving the things a name in 1967, to Cygnus X1 in the 70s, to the patient tracking of stars around Sagittarius A star through the 90s and 2000s, to an actual photograph in 2019. A century-long journey from pure mathematics to direct observation. That's the power of general relativity. It predicted something so extreme, so far beyond everyday experience, that it took 100 years of technological progress before we could even check whether it was right. And it was right. But black holes, as spectacular as they are, aren't the only prediction of general relativity that took decades to confirm. There's another one, and in some ways it's even more profound because it involves the fabric of space-time itself, rippling, vibrating, carrying energy across the universe at the speed of light. Einstein predicted them in 1916, just months after completing general relativity, and then spent years going back and forth about whether they were real or just mathematical artifacts. He actually published a paper in 1936 arguing they didn't exist, before a reviewer, who turned out to be the physicist Howard Percy Robertson, pointed out an error, and Einstein revised the paper to say they did exist after all. The whole episode is a wonderful reminder that even Einstein could get confused by his own theory. The things I'm talking about, of course, are gravitational waves, and the story of how we finally detected them is one of the most remarkable in all of physics. Because gravitational waves are, without exaggeration, the faintest signal anyone has ever tried to measure, and the machine that finally caught them is one of the most extraordinary pieces of engineering ever built. Let's start with what gravitational waves actually are, because the concept is beautifully simple, even if the detection is nightmarishly hard. Remember how we talked about general relativity describing gravity, not as a force, but as the curvature of spacetime? Mass and energy warp the fabric of the universe, and everything moves along the curves that warping creates. Well, gravitational waves are ripples in that fabric. Imagine dropping a stone into a still pond. The surface of the water deforms where the stone hits, and then that deformation propagates outward as a wave. Gravitational waves work the same way, except instead of the surface of water, it's the structure of space-time itself that's rippling. When something massive accelerates, two black holes spiraling toward each other, two neutron stars colliding, a star exploding asymmetrically, it sends ripples racing outward through the universe at the speed of light. As those ripples pass through a region of space, they stretch it in one direction and compress it in the perpendicular direction, then reverse, oscillating back and forth. Space itself is doing this. The distances between objects physically change as the wave passes through. Now here's the thing that makes this so incredibly difficult to detect. Gravity is by far the weakest of the fundamental forces. Electromagnetism is something like 10 to the 36th power times stronger than gravity. So gravitational waves, even from the most violent events in the universe, are unimaginably faint by the time they reach Earth. The amount of stretching and squeezing we're talking about is on the order of 1 part in 10 to the 21st. Let me put that in perspective. If you had a ruler stretching from Earth to the nearest star, about 4 light-years away, a gravitational wave from a pair of merging black holes would change the length of that ruler by less than the width of a human hair. That's the kind of sensitivity you need. And you need to achieve it here on Earth, where the ground is constantly vibrating from traffic, ocean waves, earthquakes, wind, people walking around. Everything is shaken, all the time, at amplitudes millions or billions of times larger than the signal you're trying to detect. So for decades, most physicists thought this was simply impossible. You couldn't build a detector sensitive enough. Einstein himself was ambivalent about whether gravitational waves carried real energy or were just coordinate artifacts, mathematical ghosts that appeared in some ways of writing the equations, but didn't correspond to anything physical. That debate actually persisted well into the 1950s. It wasn't fully settled until 1957, at a conference in Chapel Hill, North Carolina, where the physicist Richard Feynman presented what's now called the sticky bead argument. It's a beautiful thought experiment. Imagine a rod with two beads on it, free to slide back and forth. If a gravitational wave passes through, it will stretch and compress space, moving the beads relative to each other. If the beads can slide, friction between the beads and the rod will generate heat. And heat is energy. So the wave must be carrying real, physical energy. It sounds almost too simple, but it was exactly the kind of clear thinking that cut through years of mathematical confusion. Gravitational waves are real. They carry energy. In principle, they can be detected. The first person to seriously try was Joseph Weber, a physicist at the University of Maryland. In the 1960s, Weber built what are now called resonant bar detectors, essentially large cylinders of aluminum, about 2 meters long and 1 meter in diameter, weighing several tons. The idea was that a passing gravitational wave would make the bar vibrate very slightly at its resonant frequency, and you could pick up that vibration with sensitive piezoelectric sensors attached to the surface. Weber was a remarkable character. He'd been a naval officer in World War II, survived the sinking of a ship, and came to physics relatively late. He was bold, creative, and absolutely convinced that gravitational waves could be detected with the technology available at the time. In 1969, Weber announced that he was detecting gravitational waves. He claimed to see coincident signals in two detectors separated by 1,000 kilometers. One in Maryland, one at Argonne National Laboratory near Chicago. The physics community was electrified. If true, this was one of the greatest experimental achievements in history. But here's where the story takes a painful turn. Other groups around the world built their own Weber bars, tried to replicate his results, and couldn't. Nobody else saw the signals Weber was seeing. The expected rate of events from known astrophysical sources was far too low to explain what Weber claimed to be detecting, and the sensitivity of his bars, when carefully analyzed, seemed insufficient. Over the course of the 1970s, the consensus shifted firmly against Weber. Most physicists concluded that he was seeing noise, not gravitational waves. Weber never accepted this. He continued to insist his detections were real until his death in 2000. It's a genuinely sad story, because Weber was the pioneer who got everyone thinking seriously about gravitational wave detection, who trained many of the people who would go on to build the detectors that actually worked. He was right that the quest was worth pursuing. He was almost certainly wrong that he had succeeded. But Weber's work inspired a completely different approach, one that would eventually lead to success. In the early 1970s, several physicists, most notably Rainer Weiss at MIT and independently a group in Europe, began thinking about using laser interferometry instead of resonant bars. And this is where the engineering gets truly extraordinary. The basic concept of a laser interferometer for gravitational wave detection goes like this. You take a laser beam, split it in two using a partially reflective mirror called a beam splitter, and send the two beams down, two long, perpendicular arms. At the end of each arm, a mirror reflects the beam back. The two beams recombine at the beam splitter, and because light is a wave, they interfere with each other. If the two arms are exactly the same length, you can arrange the interference so the beams cancel out, destructive interference, and no light reaches your detector. But if a gravitational wave passes through, it stretches one arm and compresses the other. Now, the arms are slightly different lengths. The beams travel slightly different distances. They no longer perfectly cancel. A tiny amount of light leaks through to the detector. By measuring that light, you can infer how much the arm lengths changed, and therefore, the strength and shape of the gravitational wave. Simple in concept, absolutely diabolical in practice. Rainer Weiss wrote a landmark paper in 1972. Technically, it was an internal MIT report, a quarterly progress report for a research group, that laid out the entire scheme in extraordinary detail. He didn't just describe the concept. He went through every single noise source he could think of, every way the measurement could go wrong, and estimated whether each one could be overcome. Seismic vibration, thermal noise in the mirrors, fluctuations in the laser light itself, residual gas molecules in the beam path scattering the light, radiation pressure from the laser pushing on the mirrors. He analyzed them all, worked out what you'd need to suppress each one, and concluded that yes, if you built the arms long enough and controlled the noise sources carefully enough, you could reach the sensitivity needed to detect gravitational waves from astrophysical sources. That 1972 paper is one of the most important documents in the history of experimental physics, and for years, almost nobody read it because it was buried in an internal progress report. Meanwhile, Kip Thorne at Caltech, the same Thorne who'd bet Hawking about Cygnus X1, was becoming increasingly convinced that gravitational wave detection was the next great frontier. Thorne was a theorist, not an experimentalist, but he understood the science deeply enough to know what the sources would be and how strong the signals might be. In the mid-1970s, he recruited a brilliant Scottish physicist named Ronald Drever to Caltech to lead the experimental effort there. Drever was an extraordinarily inventive experimentalist, full of ideas, sometimes difficult to work with, but genuinely brilliant at solving the technical problems that interferometric detection demanded. So now, you had two groups, Weiss at MIT, Drever and Thorne at Caltech, both working toward the same goal. And in the early 1980s, it became clear that neither group could do it alone. The detector they needed was going to be enormous and enormously expensive. The arms had to be kilometers long to get enough sensitivity. You needed the most stable lasers ever built, the most perfect mirrors ever polished, the most sophisticated vibration isolation systems ever designed, all operating in one of the largest vacuum systems on Earth, because even air molecules bouncing off the mirrors would create too much noise. This wasn't a tabletop experiment. This was big science on the scale of particle accelerators. In 1984, Weiss, Thorne, and Drever co-founded what would become LIGO, the Laser Interferometer Gravitational Wave Observatory. And the story of LIGO over the next 3 decades is a story of engineering at the absolute edge of what's possible, combined with institutional politics, personality clashes, funding battles, and the kind of stubborn persistence that either looks like genius or madness, depending on whether it works. The National Science Foundation eventually funded it, but it was the most expensive project NSF had ever taken on, and there were plenty of skeptics in the physics community who thought it was a waste of money. The management was turbulent. Drever was eventually removed from the leadership in a painful episode that left lasting scars. A new director, Barry Barish, took over in 1994 and is widely credited with turning LIGO from a brilliant but chaotic research project into an actual functioning observatory. Barish brought the organizational discipline and project management skills that a billion-dollar physics experiment demanded. LIGO was built as 2 identical detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. You need 2 detectors because any real gravitational wave signal should appear in both, with a slight time delay corresponding to the wave traveling between the sites at the speed of light. A noise event, a truck driving by, a tiny earthquake, would only appear in one. That coincidence requirement is what lets you distinguish signal from noise. Each detector has 2 arms, each 4 kilometers long. Inside those arms, the laser beams bounce back and forth in an ultra-high vacuum, one of the largest sustained vacuums on Earth, with the pressure inside the beam tubes about a trillionth of atmospheric pressure. The mirrors at the ends of the arms are among the most precisely shaped objects ever manufactured, polished to a smoothness of about 1 nanometer, a few atoms. They're suspended on elaborate multi-stage pendulum systems designed to isolate them from ground vibrations. The laser light is stabilized to a degree that would have seemed like science fiction a generation earlier, and the whole system is designed to measure changes in the 4-kilometer arm length of about 1/10,000th the diameter of a proton. Think about that. A proton is already unimaginably small, and you need to detect a change in distance that's a tiny fraction of that, over a distance of 4 kilometers. It's like measuring the distance to the nearest star and being sensitive to a change smaller than the width of a single human hair. That's the kind of absurd precision we're talking about, and the fact that anyone thought this was achievable, let alone actually built the thing and made it work. That tells you something about the stubbornness and ambition of the people involved. So LIGO was constructed through the late 1990s, and the initial version, called Initial LIGO, began its first science runs in 2002. And here's the honest truth. Nobody really expected Initial LIGO to detect anything. The sensitivity wasn't quite good enough. The universe is vast, and gravitational wave sources that are strong enough to register on Earth are rare in any given patch of sky. The original design was always meant to be a proof of concept, to demonstrate that the technology worked, that you could actually build an interferometer, this sensitive, operated reliably, and develop the data analysis pipelines you'd need when a real signal eventually showed up. Think of it as building the world's most expensive and sophisticated fishing rod, casting it into the ocean, and being pretty sure you wouldn't catch anything yet, but learning how the rod handled, how the line behaved in the current, what kinds of noise the waves made against the hull of your boat. You were getting ready. Initial LIGO ran through 2010 without a detection, which was disappointing, but not surprising. And then the detectors were shut down for a massive upgrade. This is the part of the story that doesn't get told enough, because it's not glamorous, but it's where the real engineering heroism lives. For 5 years, from 2010 to 2015, hundreds of scientists and engineers essentially tore LIGO apart and rebuilt it from the inside out. They replaced the lasers with more powerful, more stable ones. They redesigned the mirror suspension systems, adding more stages of vibration isolation. They installed new seismic isolation platforms. They improved the optical coatings on the mirrors to reduce thermal noise, because even the random jiggling of atoms on the mirror surface from heat is enough to drown out a gravitational wave signal. Every single subsystem was upgraded. The new version was called Advanced LIGO, and it was designed to be about 10 times more sensitive than the original. Now, 10 times more sensitive doesn't mean you can see 10 times farther. Because the universe is three-dimensional, increasing your sensitivity by a factor of 10 means you can survey a volume of space that's 1,000 times larger. 10 cubed. So Advanced LIGO wasn't just a modest improvement. It was a transformation. It turned LIGO from a long shot into something that had a realistic chance of making a detection within its first few years of operation. Advanced LIGO began its first observing run, called O1, on September 12, 2015. And here's where the story gets almost too perfect. On September 14th, 2015, just 2 days into the run, before the detectors had even been officially declared operational for science, a signal appeared. It showed up first at the Livingston detector in Louisiana, and then, 7 milliseconds later, at the Hanford detector in Washington. 7 milliseconds. That time delay was consistent with a gravitational wave traveling between the two sites at the speed of light. The signal itself was beautiful. It was a chirp, a waveform that started at a low frequency around 35 hertz and swept upward in both frequency and amplitude over about 0.2 of a second, reaching a peak around 150 hertz before abruptly cutting off. That shape, that rising whoop, is exactly what general relativity predicts for two massive objects spiraling toward each other, orbiting faster and faster as they lose energy to gravitational waves, getting closer and closer until they finally merge. The frequency tells you the orbital period. The rate at which the frequency increases tells you the masses. And when you run the numbers, what LIGO detected that morning was the merger of two black holes, one about 36 times the mass of our sun, the other about 29 times, located roughly 1.3 billion light-years away. They'd been spiraling toward each other for eons, and in the final fraction of a second, they merged into a single black hole of about 62 solar masses. Now, if you're paying attention to the arithmetic, you might notice something. 36 plus 29 is 65, not 62. 3 solar masses are missing. Where did they go? They were radiated away as gravitational wave energy, 3 times the mass of our sun converted entirely into energy in the form of ripples in spacetime in a fraction of a second. For that brief moment, the power output of that merger was greater than the combined light output of all the stars in the observable universe. That's not an exaggeration. That's the calculation. And yet, by the time those waves reached Earth after traveling for 1.3 billion years, they were so faint that they stretched and squeezed LIGO's 4-kilometer arms by less than 1,000th of the diameter of a proton, the universe's most violent event, whispering to us across 1 billion light-years, and we heard it. The signal was designated GW150914 for the date, September 14th, 2015. The team spent months verifying it, checking it against every possible source of noise, running it through independent analysis pipelines, making sure it wasn't some elaborate artifact or a blind injection test. LIGO had actually built a system where fake signals could be secretly injected into the data to test whether the team could find them and correctly identify them as fakes, a kind of fire drill for the analysis pipeline. So, when the real signal appeared, one of the first things people had to confirm was that nobody had injected it. They hadn't. It was real. The discovery was announced on February 11th, 2016, and it was one of those rare moments in physics where the result was simultaneously expected and astonishing. Expected because general relativity had predicted gravitational waves 100 years earlier, and the indirect evidence from the Hulse-Taylor pulsar had been rock solid for decades. Astonishing because actually detecting them directly, actually building a machine sensitive enough to feel space-time stretch, that had seemed almost impossible for so long. And the fact that the first signal came from a binary black hole merger was itself a surprise. Many physicists had expected the first detection to come from merging neutron stars, which were better understood and had been observed indirectly. But the universe had other plans. It handed us 2 black holes, objects that don't emit light, don't show up in any telescope, and are only visible through gravity itself. The first thing gravitational wave astronomy ever saw was something that only gravitational wave astronomy could see. There's a kind of poetic completeness to that. In 2017, Rainer Weiss, Kip Thorne, and Barry Barish were awarded the Nobel Prize in Physics. And you could make a case that it was one of the most well-deserved Nobels in the history of the prize. Not just for the discovery, but for the sheer persistence. Weiss had written that first detailed proposal in 1972. Thorne had spent decades building the theoretical framework and recruiting the right people. Barish had taken a troubled project and turned it into a functioning observatory. From concept to detection was over 40 years. Entire careers were spent on this by people who had no guarantee it would ever work. But here's the thing. GW150914 was just the beginning. Since that first detection, LIGO, along with the European Virgo detector and later the Japanese Kagra detector, has observed dozens and dozens of gravitational wave events, binary black hole mergers of various sizes. And then, on August 17th, 2017, came the event that really opened up a new era. GW170817, the merger of 2 neutron stars. This one was special because neutron star mergers, unlike black hole mergers, produce light. A lot of light. So when LIGO and Virgo detected the gravitational wave signal, they sent out an alert to astronomers around the world, and within hours, telescopes across the electromagnetic spectrum, gamma ray, X-ray, ultraviolet, optical, infrared, radio, were all pointed at the same patch of sky. They found it, a kilonova in a galaxy called NGC 4993, about 130 million light-years away. For the first time in history, the same astrophysical event was observed in both gravitational waves and light. Multi-messenger astronomy, they call it, and it's exactly as revolutionary as it sounds. It's like spending your whole life only able to hear the universe and suddenly gaining the ability to see it at the same time. That neutron-star merger also settled a long-standing question. Where did the heaviest elements in the periodic table come from? Gold, platinum, uranium. Elements heavier than iron can't be forged in ordinary stars. For decades, the leading theory was that they were produced in supernova explosions, but the numbers never quite worked out. The observations of G 170817 showed clear spectroscopic signatures of heavy elements being produced in the aftermath of the neutron-star collision, a cosmic forge of unimaginable violence, spraying freshly minted heavy elements into space. The gold in any ring on your finger, the platinum in a catalytic converter, the uranium in a nuclear reactor. Much of it was likely produced in ancient neutron star mergers billions of years ago, scattered into the gas clouds that eventually collapsed to form our solar system. You are, in a very literal sense, wearing the debris of colliding dead stars. And so here we are. Gravity, this thing that seems so simple, so obvious, so everyday, turns out to be the deepest, strangest, most subtle force in nature. It's the one that Newton figured out well enough to predict the motion of planets and cannonballs, but not well enough to explain what it actually is. It's the one that Einstein reimagined as the curvature of spacetime itself, a geometric property of the universe, rather than a force pulling through empty space. It's the one that bends light, slows time, creates black holes, and ripples through the fabric of reality when massive objects collide. And yet, for all we've learned, gravity remains in some ways the most mysterious of the fundamental forces. It's by far the weakest, absurdly weaker than electromagnetism, or the strong nuclear force, or even the weak nuclear force. A tiny refrigerator magnet can hold up a paperclip against the gravitational pull of the entire Earth. Why is gravity so weak? Nobody knows. It's one of the great unsolved puzzles in physics. And gravity is the one force we still don't have a quantum theory for. We have quantum electrodynamics for electromagnetism, quantum chromodynamics for the strong force, the electroweak theory for the weak force. But quantum gravity remains elusive. General relativity and quantum mechanics, the two greatest theories of the 20th century, are fundamentally incompatible at the deepest level. They both work spectacularly well in their own domains, but when you try to apply them both at once, at the center of a black hole, or at the very first instant of the Big Bang, the math breaks down. The equations give you infinities, which is nature's way of telling you that you're missing something. String theory, loop quantum gravity, various other approaches. Brilliant people have been working on this for decades, and we still don't have a complete answer. Maybe we will someday. Maybe someone listening to this right now, drifting off to sleep, will be the one who figures it out. Stranger things have happened. Einstein was a patent clerk, after all. But for tonight, here's what I want you to sit with, or rather, drift with. Gravity is the reason you're lying where you're lying right now. It's holding you gently against your bed, pulling you down with a force that's been described and refined by some of the greatest minds in human history, from Aristotle's first fumbling guesses to Newton's elegant equations, to Einstein's breathtaking reimagining of space and time as a single dynamic fabric. It's the force that holds the moon in orbit around the Earth in orbit around the sun in orbit around the center of the Milky Way. It gathered the primordial hydrogen clouds into stars, squeezed those stars until they ignited, forged the elements in their cores, and when the biggest ones died, it crushed their remains into neutron stars and black holes. It ripples through spacetime when those remnants collide, carrying information across billions of light years to detectors built by curious, stubborn, extraordinary human beings. Every single thing about your existence, the ground beneath you, the air above you, the planet you live on, the star that warms it, the atoms in your body that were cooked inside ancient stars, all of it is shaped by gravity. It's the quietest force, the gentlest, the most patient. It never stops, never shields, never switches off. It just curves space-time, steadily, everywhere, always, and lets the universe unfold along those curves. So let that hold you now. Let the same force that bends starlight and spirals galaxies be the thing that keeps you settled and still. You don't need to understand all of it. Nobody does. Not yet. But you know more than you did an hour or two ago, and the universe is a little less mysterious and a little more wonderful than it was before you closed your eyes. That's enough. That's more than enough. Let it go now, all of it. The equations, the black holes, the interferometers, the ripples in space-time. Let them drift. You'll carry them with you into sleep, and maybe into tomorrow. And maybe, just maybe, you'll look up at the night sky a little differently the next time you're outside in the dark. But for now, just rest. Gravity's got you. It always has.